This is my most important video if you're learning quantum mechanics or about interpretations. There's a physical space with particles, and there's an abstract configuration space with wave functions. Textbooks often mix these two in the same graph, giving the impression that they're the same thing, but they're not. We start with the single and double slit experiments. We shoot particles at a wall, and the particles that go through a slit are detected at a screen. Now, classically, particles go in straight lines and are detected at a location straight behind the slit. But in quantum mechanics, we see something else. First, with a single slit, the particles spread out, which is called diffraction. And with two slits, we get an interference pattern. Now, we know where the particle started and where it was detected. These are small, well-defined locations, which is why we call the particle a particle. But quantum mechanics doesn't tell us anything about the trajectory in between. This is why we show the particle as transparent. Here's where the confusion starts. Quantum mechanics does give us a wave function, which tells us the probabilities of detecting the particle at various distances. The problem is that we often draw the wave function in the same graph, like this, where we have diffraction, or like this, for interference. There are a couple of problems with this image. The first is a minor problem with the animation. The wave function actually is non-zero, only in a narrow band. This is what it really should look like. The second problem is more serious. It looks as if the particle changes into a wave and then turns into a particle again. But this is not what quantum mechanics says. The problem here is that it looks like the wave function lives in physical space. But it doesn't. It is in something called configuration space, which is an abstract mathematical space used for calculations. So what is this configuration space? Let's first look at a simple case in one dimension, and where we know exactly where the particles are located. Each particle has a coordinate. Let's call them x1 and x2. Then that gives us one single point in configuration space. When the particles move, the point in configuration space moves. If we add another particle in physical space, we add another dimension in the configuration space. And if we have a zillion particles, then we have a zillion dimensions, but we still have only one single point in configuration space. Let's say we're not sure where the blue particle is. It could be in one of three locations. Then our wave function will also split into three parts. We have a superposition of three locations in configuration space. In physical space, we still only have one particle, but we're uncertain about the location. If we now measure the location, the wave function collapses to a single point. Now let's use a single particle, but in two dimensions. Then the configuration space still has two dimensions. Let's have a lot of uncertainty in the particle's location in X. When the uncertainty is essentially continuous, then in configuration space we get a continuous function of X. This is why we call it the wave function. In the case of a single slit, we get diffraction like before, but the wave function is now in configuration space. The wave function is just a mathematical tool that tells us what we can measure in physical space. Let's move all the way up to the screen, and when we detect the location, the wave function collapses. And with two slits open, we get interference. But again, the interference happens in configuration space. We now have all the basic images I wanted to show you, but let's do one more about decoherence. Let's say we want to detect which slit the electron goes through. We can do this by putting a proton between the two slits. Since the proton moves in one dimension, we add one dimension to the configuration space. With a single slit, the proton is attracted to that slit. In configuration space, the wavefunction moves down. And if the other slit is open, the proton moves in the opposite direction, and the wavefunction moves up. With two slits, the proton can go in both directions, and the wavefunction divides into two parts. And here's the important thing. One part goes up and one part goes down. And since the two parts don't overlap, we no longer get interference. This loss of interference happens in configuration space and is called decoherence. Decoherence is popular because it solves part of the so-called measurement problem. Okay, so take-home messages. The wavefunction lives in configuration space, not in physical space. Particles live in physical space, while information about the particle lives in configuration space. The particle is not a wave packet. They are different things in different spaces. When the wave function smears out, that just means we lack information about the particle. It doesn't mean that the particle actually exists in multiple locations. Uncertainty and measurement occur in physical space. Superposition and collapse occur in configuration space. If you're still tempted to think of the wave function as living in physical space, you need to be aware of one more thing. If we had two particles at the same time, they would each have a private wave function, and they don't react to the wave function of the other particle. This is very different from a physical field, like the electromagnetic field. Here we have several particles, and they all react to the same electromagnetic field. However, that's not the case with the wave function in quantum mechanics, as we have seen. And that's it. This has been a lot of stuff, and I recommend that you watch the video again and pay attention to all the details. I'll see you in the next video. For more videos, go to physicsisnotweird.com, and I'm Eyvind Bernander.